All right, recording is on. Okay, good morning. So last time we derived like what is the induced flow using this kind of method, right, for a rectangular wing. So what we have done is we have taken the rectangular wing and using the lift per cross section, the lift per span to figure out how much circulation there is on this wing, right? And from that circulation, which was a single vortex coming from one wingtip to the other wingtip, we figured out what is the circulation of the wingtip vortices that comes out of the wingtips. And using the strength of these circulations, we figured out how much downwash is on various locations of the wing. And we know from the downwash, right, the downwash essentially tilts the vector of lift. And from how much that vector of lift is tilted, we can calculate how much induced drag there is on this wing, right? So this kind of a method is used not only analytically to calculate the induced drag. For example, if you are instead of calculating the induced flow on just the 4 locations as we did last week, as we did on Monday, if we calculate the induced downwash everywhere, okay, as a function of the y location, so this is the y-axis, and we perform an analytical integration, we can actually figure out what kind of a wing would minimize the amount of induced drag for the fixed amount of lift. And that turns out to be an elliptical distribution. All right, so something you can read. And I would say this is nowadays, the analytical methods nowadays are less and less relevant, because today, if you want to compute what is the optimal distribution, you can actually perform a numerical calculation by discretizing the wing into many, many small segments, right? And now, if we know the distribution of the lift, then the amount of circulation on each section of the wing is going to be different, right? And from the difference in the circulation in section 1 and section 2, we can compute how much vorticity comes out in between section 1 and 2, right? So this is going to be a vortex. Okay. Similarly, we can compute from the difference in the lift in 2 and 3. We can compute how much vorticity coming out of the gap between 2 and 3. So essentially, we can integrate the induced downwash by all these vortices. We can add them together and compute how much downwash is on each section of the wing, and then sum them up in the computer, and then we get how much induced drag there is. And then we can wrap this whole thing into an optimization routine and optimize not just for the minimum induced drag, but also take into consideration of like stability, right? How much, what is the rigidity of the wing, right? I mean, if you have different span-wise loading, as we're going to do probably in the project section, you're going to have a different estimate of how strong the wing has to be, and therefore how much the wing has to weigh. Okay, so you can basically, the optimization procedure can take all these different considerations into a single objective function, and the result is going to be a lot more practical than the traditional analytical method that gives you, okay, elliptical distribution is the optimal from purely aerodynamic consideration. So this is the most, I would say, the most simple way of computing the flow in 3-dimensional bodies. There are more advanced ways that not only takes into consideration of how strong the vortex come out of the every section to be, but also how these vortices actually is going to move in the three-dimensional space. Remember, if you look at this model, it assumes that the vortex is coming out of the wingtip and in between these sections just go straight downstream to infinity. This is roughly true if the loading on the airplane is not that high, right? So if you have a glider, that actually works out pretty well. But if you have high loadings, you can see that all of these vortices are actually going to induce a pretty strong flow, right, compared to the free stream. So if your induced flow divided by the free stream velocity is not infinitesimally small, then these vortices actually are going to move, right? These vortices would move not only by the free stream flow, but also by the induced flow themselves. So this assumption is no longer true. Also, what is not going to be true is for things that doesn't just go in a single direction. For example, if you have a wing that rotates, on a helicopter, for example, right, the vortices coming out of the a helicopter blade is not going to go back to infinity. They are going to basically go around with whatever flow is on the helicopter. So people developed more advanced method from the lifting line theory. So this is called the lifting line theory that assumes all the vortices just go downstream to infinity. People developed the vortex lattice method. So what's the difference? The difference is that we no longer assume these vortices go downstream to infinity. Instead, we are going to be approximating this string of vortices using individual elements of pretty much rectangular vortex rings. So what is a vortex ring? Have you go to aquarium and seen like whales spit out rings of vortices?
Not in the aquarium, but in real life.
In real life, okay. So what kind of stuff have you seen?
So when a dolphin shoots air out the blowhole, there's a little ring that floats out.
Yeah, that's pretty fun to watch, right? And if you go to YouTube, there are all kinds of crazy videos of vortex ring generators, right? It's basically a big air gun. If you release a membrane, and when the moisture is high enough, you can actually see the vortex ring pushed out, and it can go pretty far. So these are essentially vortex rings that has the air going downward. So literally, we are approximating the air downstream of an airplane, as if the airplane wing is a device that continuously shoots vortex rings in the downward direction, right? So it's like this vortex ring, as we have seen from the equation obeyed by vorticity, is going to go with the flow, right? So we are solving equations that tracks how this vortex ring is going to move, okay? How it's going to deform. Maybe it's going to be stretched in a certain direction, squeezed in another direction. Maybe it's going to be rotated, right? We're going to be tracking how each vortex ring moves. But as all the vortex ring moves downstream, this airplane wing is continuously generating new vortex rings, right? It's like literally the wing is like a dolphin spitting vortex rings in the downward direction in a continuous way, okay? And how much vortex ring it spit down per unit time is actually computed by how much lift, right? What is the circulation around the airplane wing, right? So these kind of stuff can be done not only for steady state airplane flight, but for unsteady maneuvers, right? So this kind of vortex lattice method, being able to track how these rings move and deform as a function of time, is superior to the lifting line method, especially when the loading is high and when you have unsteady aerodynamics. All right, questions? So this is, I mean, one of the objectives of this course, aerodynamics, is going to help you in the future when you are faced with the choice of various tools. Most of them are computational tools to analyze the force and the stability and the efficiency of different aircrafts at different scenarios. You should be able to choose, you should be able to understand what underlies the assumptions, right, behind all these tools, and to figure out for this scenario, this tool is probably the best. All right, so here we are laying out the difference between the lifting line method and the vortex lattice method. Lifting line method is basically what you did back on Monday on the blackboards. Vortex lattice method probably requires a computer, right? You don't want to figure out. You don't want. I mean, there is still the principle of superposition. We are still assuming potential flow and incompressible flow, but you have to sum up the contribution from all these vortex rings, not only from this section but from all the sections going out to infinity. All right. So let's actually see how this vortex lattice method might apply to a completely different scenarios. That is helicopters. So the simplest scenario for a helicopter is when it is at a hovering condition. So let's see. Sound. And look at how these vortices are moving.
Volume rendering has applied to the ongoing numerical wave breakdown research. This visualization technique has provided a new perspective on the existing data by allowing the entire wake to be visualized at once instead of using surface-based isosurfaces or sliceable wakes. The physics behind the wake breakdown process are more clearly seen in this format. Note that the wake sheet, tip vortex, and all secondary structures are clearly visible using a single volume rendering. Here is a
So here is the so-called the tip vortex, right? So the blade is generating lift, and so there is circulation if you draw a contour around every individual blade, right? And then, as we have studied, the kinematics of vorticity does not allow any circulation, any vortex, which in this case lies within this blade, to end at any point. So the same amount of circulation has to come out as a vortex. So that's the tip vortex. That's clearly visualized over here. All right. One of the interesting things is we are going to analyze a little bit later is that initially the tip vortex doesn't actually go down. It seems to be moving towards the center of the rotor disc, and only after the next blade comes by, that tip vortex is pushed down. So if you keep looking,
rotor case that applies a fixed Cartesian off-body mesh to the wake.
Right. So initially it doesn't move down; it moves inward, and then the next one pushes it down.
Into
right?
the helical wake and forms braids. Note how the tip vortex strength becomes uneven along the core as the wake gauge increases. The interplay of these two wake structures eventually becomes unstructured vortical flow with no remnants of the tip vortex visible in that.
Okay, so another thing is the secondary vortex she was talking about. What is that? Remember, when one blade comes over, right, it is actually swiping through the flow where there is already a vortex that was generated from the previous blade. I'm fine, I'm recording this. Yeah, thanks. Yeah, so it is a swiping through a tip vortex that's generated by the previous flow. So this vortex rotates in what direction? So can somebody think about what is the sense, or how does this vortex rotate?
So if I'm looking at this vortex,
Does it rotate that way, or does it rotate that way? Like, what is the flow around it?
The first one is it.
The first sense?
Yeah.
Yes, that's right. I mean, the way I think about it is, what is the sense of the circulation around this rotor blade? All right, a rotor blade is generating positive lift, right? So the flow above it has to go faster, right? Low pressure. So if you look at this blade, the circulation has to be that way, right? Okay, and then the vortex coming out of the tip is a continuation of the circulation on the blade. So when you think about this and it comes back, the circulation has to be like that. All right? Okay, so now as we remember, this vortex is moving inward. So as the next blade swipes by, this vortex actually induces a different angle of attack in different sections of the next blade, right? So if this is my next blade and I already have a vortex rotating this way, not at the tip, but a little bit inward of the tip, would it increase or decrease the angle of attack in the small tip section beyond the previous vortex? What is the induced flow like in the tip section when I have a preceding tip vortex? Up, exactly, right? A vortex rotates that way. So it induces an upward flow at the tip and a downward flow in the inner section of the blade. So there is a discontinuity almost in the angle of attack, and as a result, a discontinuity in how much lift is generated per span of the blade. And that discontinuity in lift, right, also comes out as what's known as the secondary vortex. Okay, it's almost like in between the section of a airplane wing in landing configuration with a flap and without a flap, right? So the difference in how much lift is there per span comes out as a vortex, in this case a secondary vortex.
This unstructured flow region does not extend all the way up to the rotor plane, but eventually settles on the final wake state. This final wake state is visible around the current point in this movie.
And all these complex structures down there is really a result of the three-dimensional vorticity equation. Remember, we are talking about all these vortex stretching and the vortex rotation, right? Due to the term that we know as the omega dot with the gradient of velocity, right? How a vortex moves as if it's a material line. Now, if I have many vortices interacting with each other, they actually stretch each other and rotate each other. As they get stretched, the vorticity gets thinner but stronger, right? And this is the primary mechanism of what's generating turbulence in three-dimensional flow. And this is actually why turbulence doesn't exist. At least the classical sense of turbulence doesn't exist in two-dimensional aerodynamics. But in three-dimensional aerodynamics, as soon as you have multiple vortices interacting with each other, you get turbulence actually pretty quickly, right? And that's what's happening over here. Okay, so of course, if you want to use the vortex lattice method, you have to do a little bit approximation, right? So you cannot have a infinitely fine vortex lattice that is going to allow these vortices to get distorted, right? So basically, you have to have a minimum resolution when these vortex rings get distorted too much beyond the recognition. You have to merge them and diffuse them as if there is viscosity. But once you do that, the flow around the helicopters can be pretty well computed by these vortex lattice methods, right? So essentially, you just treat it as an airplane, and as the blade rotates, no matter in hover condition or in forward flight condition. In forward flight condition, what's a little bit more interesting is that the lift is going to change as a function of time. So the strength of the vortex coming out even from the same section would change as a function of time. So the vortex ring here would not cancel with the vortex ring here, even on this dimension, right? So you would get actually a continuous sheet of different strengthed vortices. All right, so this is really the extent to which the vortex lattice method can be used. But before we just completely trust the computer to do all these calculations, I want to give you a sense of really what the flow around a hovering helicopter is like. So to do that, we want to really make even more assumptions and get to the simplest possible answer. So that is something I want you to start working out on these blackboards and on the papers. So I'd like you to figure out in a very, very simple scenario, even without considering any helicopter as individual blades, right? Just to think about the blade revolving around the disk as a single device that continuously generates a push on the air as the air goes through this rotor disk. So basically ignore this unsteady motion of the blades and just think of the rotor as a blurred disk, right? Imagine that the rotor rotates so fast that like even the air wouldn't see the individual blades. Essentially, the assumption is, okay, when the air is at infinity, the velocity is 0, right? The helicopter is hovering. And this blade disk essentially needs to suck air from 0 velocity to this point. Okay? At this point, the air gets sucked down with a velocity of v. All right? Okay? Now the tricky thing is that, as you have seen in the video, as the air accelerates through the rotor disk, there is still an inward motion of the air, right? And basically, the stream tube keeps shrinking as you go further downstream. So, if the stream tube keeps shrinking, would the velocity far downstream be higher or lower than the velocity of air going through the disk? Higher, right? We are still in the incompressible world, right? We are going to go to compressible world probably next week, but like now we are still saying that v times the area, velocity times area is constant. All right. So here are 3 questions I want you to answer, and once you have these answers to the 3 questions, we can derive some wonderful conclusions, actually. So first of all, what's the relation between v, w? V is the velocity across the rotor disk. W is the velocity far downstream. A, which is the area of the rotor disk, and the area of the induced downward far below the rotor. So we denote this area, let's say, as A prime. So let's imagine this area as A prime. All right. And we're assuming the far upstream, the velocity is 0. All right. Okay. That's the first question. Hint is conservation of mass. I mean, this is a wonderful application of the conservation principles. Second question is, what is the relationship between rho w, which is the velocity over here, A prime, and the thrust? That's a wonderful application of conservation of momentum, right? You draw a very large control volume around the whole thing so that pressure actually doesn't come into play. When you draw it far enough, the pressure around the control volume is pretty uniform. And third is, what is the relationship between rho w A prime and the power, right, by the rotor? So hint is conservation of energy. So please go ahead and start working on these equations.
Oh, baby shark. Rho AV equals WA prime. Get it. Oh yeah. Yeah. And then isn't that how we did the power? Yeah. And we need to get TV on one side.
No, but we're not supposed to have the. Oh, I was. But for 2, we're not supposed to have these.
Yeah, you're working on 2?
Yeah.
Well, actually,
One second. So what is the control volume? I think most of the class got it. Most of the class got it, right? So V is going to be, can somebody tell me, square root of what? T 2 rho A, right? Okay. And the power, right, which is can be said as TV is equal to, well, basically I make a cube on the T, right? Because that's multiplied an additional T. So 2 rho A. Right? That's the power. All right. So this is a very interesting result. If I increase the power by 1%, for example, like how much additional thrust do you think I get if A and rho doesn't change? Anybody still remember fractional sensitivity? If I increase 1% of the power, right? So if I turn the engine a little bit higher, right? So the engine outputs 1% more power.
0.66%.
Yeah, 0.67%, right? So I get less than proportional the amount of thrust increase. So this is actually another very interesting result, is that there is a 2 rho A in the denominator, of course square rooted. That means if I'm, for example, flying on Mars, what difference am I making? I have like 1% of the amount of rho, right? Okay, so if I have exactly the same helicopter and I want to produce exactly the same amount of thrust as on Earth, I need 10 times the power, right? Okay, how to compensate for that? Well, I can have a bigger rotor area, right? So a bigger rotor area always helps to reduce the power for the same thrust. So especially if you want to design something with power being the primary concern or power being the primary constraint, and you want to lift heavy weight, what do? Well, of course, we can't really change rho, so we increase the area. So imagine you are being tasked to design a helicopter that can hover while carrying the weight of a human, while the only power input is the human itself. What would you do? a large rotor, right? Have you ever seen a design like that people try to do? Okay, so that's actually something I think done in Canada a few years ago. They actually built something that a cyclist.
Altitude over attempts. Flight test 11, altitude record.
Flight test 11, altitude with Henry.
So look at how big this thing is.
Oh my god. Holy moly. Bring it down, bring it down.
Well, one of the interesting thing about this flight is that as you also calculated, right, the induced velocity, the velocity that goes down the rotor plane, I mean, this is a massive, 4 massive rotors, right, huge A. As you've seen, the velocity of the flow downward is square root of t, which is small, right? Human is not that massive, divided by 2 rho times A. So the induced velocity, the velocity going down, is also very small. So as this helicopter is operating, the flow in the whole stadium is actually recirculating. I mean, at some point, the whole stadium starting to have a very slow flow that's recirculating, but that's actually comparable, starts to be, to the velocity that goes down the rotor. So at some point, although this poor guy is cycling like hell, it doesn't go up anymore because the flow in the whole stadium is starting to go around. So anyway, so he would have a better record if he's doing this on the open field as opposed to inside the stadium. All right, so this is so far what I want to cover about three-dimensional flows. And as you can see, there is a little bit of analysis we can do about reasoning about the vortices and the induced flows, but not that much. Okay, a lot of the more three-dimensional analysis is done nowadays by computers. You have to do a lot of calculations, adding things together. The nice thing is the principle of superposition when you are considering only potential flow, right? So basically you can think about all these vortices, either vortex lines or vortex rings, and add the effects together to form a flow field. Of course, you have to have a computer to laboriously add all of them together to calculate the flow field. But at least now you understand the principles behind all these computer programs that does all this work. Now I want to, because of we are kind of constrained on time, we want to go to module 3, viscous and compressible flows. So this is a new section that will really the last section that's kind of introducing you to the more non-ideal stuff, the more complex stuff we wish we don't have to deal with, but we have to deal with in aerodynamics. So we have done with three-dimensional vortices, lift-induced drag. And for me, a better way to think about it is not really lift-induced drag, but lift-induced power, right? I mean, when we think about airplanes, it has induced drag. If you multiply the induced drag with forward velocity, you get how much power you have to input to form the kinetic energy, to feed the kinetic energy you leave at the wing. It's actually the same thing for the hovering helicopter we just analyzed, right? We figured out how much power the helicopter has to provide to feed the amount of kinetic energy that leaves the helicopter, that goes downward in this case. So this is like I think my most intuitive way of thinking about induced either drag or power, not just for airplanes but for helicopters and combination of airplanes or helicopters if you think about more interesting designs. So okay, so now we are going to viscous and compressible flows. The first thing we are going to learn about is actually viscous flows. So as we have seen, viscosity can be ignored for most of the flow field if the flow does not separate from anywhere. Okay, so that's a big if. Especially for airplanes and airfoils, we know that the flow is going to separate if you put it at high enough angle of attack. So the question is really, what scenario would the flow start to separate? And more importantly, what can we do to prevent the flow from separating? And if we cannot prevent the flow from separating, how would the separation affect the performance, like efficiency and stability, and how much lift you can provide for the airplane? So that's the thing we are going to be focusing on first. And then we are going to go to transonic and supersonic flight, look at a compressible flow and the shock. I don't think we'll have time to look at too much on unsteady flows and aeroacoustics. I mean, these are nowadays mostly regimes of computational fluid dynamics anyway. So, I mean, there is a lot of theory behind that, but to get any result on realistic designs, you do computations. All right, so let's focus on viscous flows and boundary layers first. So what causes stall? So remember when we were looking at the performance of different airfoils, right? This is the symmetric NACA 0012 airfoil put on top of a fuselage. At high enough angle of attack, at high enough lift coefficient, we see that the drag increases pretty dramatically. It deviates from this seemingly parabolic line, right? And increases a lot more than at lower angles of attack. And the L over D also drops accordingly. And when we visualize the flow field, it turns out that there are two bubbles close to the junction between the wing and the fuselage that has clearly much lower skin friction. And the direction of the flow, instead of going downstream, is now going primarily upstream near the surface. So that's stall. And if you look at the three-dimensional flow field, you're going to see the boundary layer, instead of staying attached like over here, actually goes into the three-dimensional space. And there is a viscous wake that's much larger than the viscous wake coming from the attached sections. So today we will start looking at the behavior of the boundary layers and what causes a boundary layer to separate. What forces affect the boundary layer? Well, it's all the forces we have studied so far plus viscous force, right? So what are actually all the forces we have studied so far that affects the flow? In the previous section, in the incompressible potential flow section. Pressure, right? We have studied only the pressure force. It's not simple, because the pressure force does two things. It accelerates or decelerates the flow, right? If there is a pressure gradient in the direction of the streamlines, it can also turn the flow if the pressure gradient is orthogonal to the streamlines. So there is a lot of things to think about, but the advantage in a potential flow setting is that we can use Bernoulli, and that actually simplifies the effect of pressure a lot. But in boundary layers, it turns out that pressure force is also at least as important as viscous forces. But the problem is that we can no longer just use Bernoulli and say whenever the velocity is lower, the pressure is higher. That's no longer the case. So for example, let me just take the example we just worked on for a helicopter, right? So if you look at the helicopter, so that's the rotor disc, area A, and the flow shrinks in area into A prime, and the flow goes basically parallel over here. So you might be tempted to use Bernoulli and say, okay, because the velocity is equal to 0 and the velocity is equal to W over here, the flow goes faster, therefore it has a lower pressure. That's not the case, right? Why is it not the case? Yeah?
It's no longer isentropic because you've done work to it.
It's no longer isentropic. Yeah, that's right. Okay, so yeah, so there are two ways to think about why it is not true. One way is to follow the streamlines, right? If you follow the streamlines, we know Bernoulli is always correct when you ignore viscous forces, when you follow a streamline. But the problem is when you cross here. Okay, when you cross the rotor disc, the velocity cannot change because of conservation of mass. Right? If the velocity changes suddenly across the rotor disc, if you draw a thin control volume around the rotor disc, then you would violate conservation of mass. So velocity wouldn't change. So and the pressure actually changes suddenly. Right? The rotor being pushing down actually increases the pressure. So basically there is a pressure jump without velocity jump. As a result, the stagnation pressure jumps. All right? So the stagnation pressure here is higher than the stagnation pressure here, which you follow the streamlines is the same as stagnation pressure very far away from the rotor, which is going to be the same as the stagnation pressure over here, right? So stagnation pressure here is higher. So that's one way to think about it. Second way to think about it is that in potential flow, we said that we can also apply Bernoulli across streamlines if the vorticity is 0. Here, where has non-zero vorticity? Where is vorticity non-zero in this flow field? At the tip of the rotor, correct, vorticity is not 0, right? As we saw from the video, there are tip vortices coming out. But in addition to over here, are there other places where vorticity is non-zero? Any other places other than the tip of the rotor? Where does the vortices go? Where do the vortices go? It goes down, right? So after it being shed over here, eventually where does it end up? It goes down, right? So this boundary between a flow with a velocity of W and outside it has velocity of 0, it is called a shear layer. So this is called a shear layer. It's called a shear layer because the velocity shears over here, right? I mean, there is a significant velocity gradient over here. So in this case, the flow, if you zoom in, the flow looks like that. So if you zoom in over here, right, on the left-hand side, the velocity is low. On the right-hand side, the velocity is high. So you have a significant velocity gradient in the x direction and a significant y velocity gradient in the x direction, and no x velocity gradient in the y direction. Therefore, vorticity cannot be 0, right? Okay, vorticity is the difference between the x derivative of y velocity and the y derivative of x velocity. So if y derivative of x velocity is equal to 0 and the x derivative of y velocity is not equal to 0, then vorticity will not be 0. You cannot apply Bernoulli across the shear layer, right? That's probably the most common novice mistake of applying Bernoulli's. Okay, so in the boundary layer, it's the same thing, except for we are turning this shear layer by 90 degrees around. So in the boundary layer, we have a wall, and on the wall, the velocity is the same as the velocity on the wall. But away from the wall, we have velocity going whichever direction it goes. So in the boundary layer, as we did in one of the homework problems, the velocity is going to be like that, right? Okay, so what forces affect the boundary layer? Let's first think about how a viscous force would affect the boundary layer. As we have done in class before and in one of the homeworks and actually in the quiz, right, if you remember, the viscous force on the wall pulls the boundary layer towards the opposite direction of the free stream, right? That force depletes momentum from the boundary layer. If the boundary layer gets depleted in momentum, does it grow thicker or thinner? Yeah? Thinner? Actually, let me ask a question, right? So this is a, let me say, this is a boundary layer profile. And I would draw a similar boundary layer with the same free stream velocity, but thinner. Like that, thinner, right? Velocity would be like that. Which boundary layer has more momentum? The red one actually has more momentum, right? Because the velocity is actually faster almost at every y location. So if the viscous force depletes momentum from the boundary, it is going to change from the red one to the green one over time. The boundary layer grows thicker, right, as the viscous force works against the flow. Okay, so now this is the viscous force. Now we have said that the pressure force is at least as important as the viscous force on the boundary layer. Well, of course, a pressure force would not be important if there is no pressure gradient. If it's a flat plate, right? If it's not on the airfoil, if it's on a flat plate, the pressure is uniform, then the pressure force is of course zero. But on an airfoil, the pressure is not uniform. There is a pressure gradient, okay? And in particular, the pressure gradient in the wall normal direction is actually not that important because because remember the boundary layer is very thin, right? So if you look at if you zoom in this scale, the curvature of the airfoil would look like zero. It's almost like looking at the curvature of Earth when you are on the human scale. The boundary layer is very thin, so when you zoom into the boundary layer, the curvature of the airfoil looks like flat, and whatever wall normal pressure gradient you have on this scale looks like nothing. Now, what's more important is the pressure gradient along the airfoil. So let's consider whether the pressure gradient along the airfoil helps or balance the viscous force. Okay, what kind of pressure gradient would balance the viscous force? Which means while the viscous force tries to thicken the airfoil by depleting momentum, what kind of pressure gradient would work against it and tries to thin out the airfoil, but by providing more momentum? Yes, higher pressure upstream and lower pressure downstream, right? That would actually push the flow in the streamwise direction, therefore works against the viscous force, right? That thins out the boundary layer. So do you remember, like when you tour the wind tunnel, right? What kind of stuff does the wind tunnel do before the test section? What was the geometry of the wind tunnel before the flow enters the test section? Yeah, it shrinks, right? Okay, and what is the consequence of a shrinking? If you think of a pressure gradient, right? What is the consequence of the section shrinking in terms of the pressure gradient along the direction of the boundary layer? Yes, it accelerates the flow, so the pressure is high upstream and low downstream. That's exactly what you need to shrink the boundary layer, right? In the test section, we don't want boundary layers. We want it to be as thin as possible. So this is what we call a favorable pressure gradient, right? It's favorable in the sense that it makes the boundary layer thinner and less significant. The opposite of a favorable pressure gradient is adverse pressure gradient. It is a lower pressure here and a higher pressure here. It helps the viscous forces, right? It helps the viscous forces to make the boundary layer thicker and thicker. And as we're going to analyze in the next lecture, the boundary layer, there is a singularity point at which if the pressure force is high enough on the already thick boundary layer, the boundary layer is going to separate. Okay, we are going to see exactly how that works in the next lecture. That happens only when the pressure force works with the viscous force, right? Basically, the pressure increasing as you go further and further downstream. So I will see you next Monday to continue discussing boundary layer separation.